A student looks at a simple motion graph of a falling parachutist. They confidently scribble down, the speed is slowing down. And just like that, they instantly lose an entire grade boundary. Why? Well, because knowing the underlying physics just isn't enough. Not if you don't know the exact words the Cambridge examiner is hunting for. We're getting right into it today. Let's dive straight into this explainer and uncover the secret mark magnets you need to actually pull those marks from the examiner and ace your next paper. So consider this extremely common scenario. A student writes, "The speed is slowing down," to describe a parachutist fall, and they get absolutely 0 marks. Now, you might be wondering, why on earth is that wrong? It seems perfectly logical, right? I mean, in the real world, the parachutist is, in fact, slowing down. But here is the brutal, unavoidable truth of Cambridge 0625 physics. Ordinary revision completely fails because it focuses entirely on what you think your teacher wants to hear. It completely ignores the highly specific mark magnets that the examiner is actually permitted to reward on their mark scheme. If the word isn't on their list, you don't get the point. It's really that simple. And honestly, this comparison brilliantly illustrates the difference in what we're talking about here. Take a look at the flawed answer. Speed slows down. It's incredibly vague, it's conversational, and, as we just established, it earns absolutely nothing. Now, contrast that with the top band answer. High deceleration as the downward sloping line represents a negative relationship. Do you see the profound difference there? It's night and day. The top band answer doesn't just state some casual, everyday observation. It actually proves the physics using geometric evidence straight from the graph, and then it wraps the whole thing up in precise examiner-approved vocabulary. That is how you secure the bag. Okay, so the absolutely crucial question is, how do you consistently generate that top band answer when you are sweating under intense exam pressure? You use this exact 4-step framework. I seriously want you to lock this into your brain right now. Step 1, identify the concept. What are we actually talking about? Step 2, cite evidence or data straight off the page. Don't invent things, just pull the numbers or visual cues they give you. Step 3, apply scientific reasoning to connect that data to the concept. And finally, Step 4, polish it all using examiner wording. No casual slang. This framework right here is your ultimate quick win for completely dismantling any complex motion data question they throw at you. Now listen closely. In just a moment, I'm going to show you a hidden examiner clue on a real graph that literally changes your entire answer. It flips it on its head. But first, you really need to understand the foundational framework that makes that specific clue obvious in the first place. Because trust me, if you don't fundamentally understand how to read the grid we're about to look at, that hidden clue is going to fly right over your head and you'll leave those marks on the table. Let's dive right into the source material. We're looking at figure 4.33. This is a classic speed-time graph for a falling parachutist. Now, complex trends in data like this, they aren't just random lines on paper designed to torture you. They are the exact, precise tools that physicists use to describe behavior and test theories in real-life situations. So let's break it down. Here, time is our independent variable. It's just steadily ticking along the x-axis. And speed? Well, that's our dependent variable, and we can see it climbing and falling dramatically on the y-axis as the jump progresses. Now, what is really interesting here, and kind of scary honestly, is how easily students get trapped by different graph types. We've recreated Table 4.2 to help lock in our evidence and avoid this trap. Notice how the entire meaning of the line's gradient completely shifts depending on what kind of graph you're looking at. On a distance time graph, a downward slope means you're returning to the start position. But on our speed time graph, that exact same downward slope means deceleration. If you panic and confuse these two distinct concepts under exam pressure, you are going to bleed marks fast. Always check your axes. Okay, let's actually apply our brand new 4-step framework directly to the parachutist's jump. I want you to focus specifically on points A, B, and C on the curve. At point A, the parachutist leaps out of the plane. Her speed increases rapidly, meaning she accelerates. But watch point B very carefully. The speed is definitely still increasing, but the line itself is flattening out. The gradient is decreasing. And a decreasing gradient here means the acceleration is lower than it was at point A. Finally, look at point C. The curve flattens completely. The gradient is 0, which means the acceleration is exactly 0. And that beautifully flat horizontal line at point C, that brings us to a massively important definition: terminal velocity. It is the constant speed reached when the acceleration of a falling object becomes exactly 0. I am begging you, please do not write "she reaches her top speed" on your paper. Write terminal velocity. That specific phrase is the exact mark magnet the Cambridge examiner is demanding to see before they give you the point. So let's map out the entire physical context of this graph chronologically, just to make sure we've got the whole story. At 0 seconds, the jump begins with some really high acceleration. Then, something drastically changes the gradient right at the 28-second mark. What happens? She pulls her parachute open. The line drops incredibly steeply, which indicates extremely high deceleration. By the time we hit 35 seconds, things stabilize again as she reaches a new, much lower constant speed. This is essentially a second terminal velocity. Finally, at 60 seconds, she lands safely and comes to a complete, very sudden stop. All right, time for a Spot the Error challenge. I really want you to actively participate here, so don't just passively listen. Based on the graph we literally just dissected, where exactly is a negative relationship shown? Think back to our table a few minutes ago and our core definitions. Take a second, lock in your answer in your head right now. Got it? Okay, let's see how you did. Let's reveal the results. Here is a very common, deeply flawed student answer. The negative relationship is at the bottom where the line is flat. Did you think this? If you did, hey, don't panic. It is a classic trap that catches so many people out. But remember our framework. We have to apply scientific reasoning. A horizontal line on a speed-time graph means zero acceleration. It means a constant speed. It absolutely does not indicate a negative mathematical relationship. So how do we fix it? Here is exactly how a Cambridge examiner corrects that specific flaw with their dreaded red pen. A negative relationship absolutely requires a downward sloping line, period. No exceptions. Mathematically speaking, it means that as the values on the x-axis, which is our time, increase, the values on the y-axis, our speed, must fall. Therefore, the correct points showing this relationship are actually from D to E to F, and then again from point G onwards. Let's actually view that exact correction right on the source graph so it really clicks for you. Look at that steep, almost vertical drop happening from D to E. That right there is high deceleration. Now, as the line curves from E to F, you'll notice it's still downward sloping, but it's flattening out, so the deceleration is lower. And finally, down at G, at the very end of the graph, we see a sharp downward spike hitting the x-axis. That's a massive deceleration as she hits the ground. The key takeaway? Every single time that line traveled downward, you are looking at a negative relationship. Let's switch gears for a quick but super essential data extraction exercise. The source material often asks something like, for how long was the parachutist traveling at exactly 5 meters per second? Well, the 25-second duration is your key here. Look at that lower flat line on the graph that represents 5 meters per second. Notice how it begins precisely at 35 seconds and it ends precisely at 60 seconds. So you just do the math. 60 minus 35 gives us exactly 25 seconds. Honestly, it is a wonderfully simple x-axis extraction, but you would be absolutely amazed at how many students misread those tiny grid lines just because they're rushing the easy marks. Don't be that student. Take your time and count the squares. As we wrap up our analysis of this really incredible source material, I want to leave you with the ultimate exam checkpoint. Seriously, write this down. This is the golden rule directly from our text. When a graph line changes, what new description or calculation is needed? Every single time that line bends, every time it flattens, or every time it drops, the physical context of the object has fundamentally changed. You must consciously stop and ask yourself this key question every single time you face a motion graph in an exam. Think about it for a second. If misreading a simple flat line can cost you an entire grade boundary, what other hidden traps are lurking in your next exam paper? Understanding exactly how to read this terminal velocity graph is a huge win, but it's really only step one. You've got the framework now, sure, but what happens when the exam throws a completely unfamiliar curveball your way and the mark scheme language changes entirely? If you stop your prep right here, you're leaving a ton of easy marks on the table. Next up in our Explainer series, we are tackling Physics 0625 examiner report mistakes and how to avoid them. You absolutely need to master the specific examiner language we decode in that next analysis if you want the top grade. Subscribe to our YouTube channel, Ace the Exams at acetheexams_IGCSE to excel in your Cambridge examinations. Click the next explainer on your screen right now to unlock even more of those critical mark magnets, and I'll see you over there.